There we go. It looks like it's working.
All right.
Okay, it looks like it's connected perfectly.
Okay, so I guess we just need to see that it's actually broadcasting something.
Yeah. If you can click the link that you sent to the members, you should be able to.
Yeah.
On my side, it looks like it's all smooth.
Yeah, I think it's working. All right, great. Are you staying for the session? It's going to be an interesting one.
Yes, I will. I just have one last question. What do you want me to title the session? If you could just send that through in the chat and then I'll edit the name.
Oh, yeah, I will type it in the chat here. It's a bit long. There it is.
Perfect. And it's session 9, am I right?
Yeah, you're correct.
Okay. Thank you so much.
Yeah, thank you.
It says the title's too long, I think. Hang
on. Just before the comma, before the joint session.
Take it away before the comma.
Just keep everything up to the comma.
Oh, okay. Perfect.
We start to analysis. Let's see if that works.
Hang on. No, it's too long still, unfortunately. It can only be 100 characters, it says.
Okay, I I haven't counted characters, but
yeah, me neither.
How about starting from the word combining?
Okay.
From combining to analysis. Let's
Perfect. And can I just say ISIE-SEM Session 9?
Yeah.
Should I include that? I'm sure I can. Okay, just see what you think. I've just put it in the chat what you think of that or if we should change it.
Just a second. Yeah, this looks good.
Okay, perfect. We can always change it again, but that's what it is for now.
Yeah, no, it looks all good to me.
Thank you. I'm looking forward to the session.
Thanks.
Good luck.
Thank you. Christoph, Sonia, I see you're already here, and I gave both of you co-host permissions, so you can check that you can share your screen, and we can check that we can hear you okay.
Hi, Tomer. Okay, I'll check.
Nice to meet you.
I can, yeah, nice to meet you too. Sorry. And yeah, I can share the screen. It's working.
All right, go ahead.
Hello, everyone.
Hey, Christoph, you're loud and clear. Sonia, I did not see your presentation. If you were trying to share it, I either missed it or it wasn't shared yet.
Uh, Hi. I didn't share. I just checked
Oh,
the
okay.
button.
Yeah. All right. So if you want to make sure that it works, go ahead. It's totally up to you. Christoph, same with you. If you want to share your screen, just to make sure that it works, go ahead.
Hello, everyone.
Do that.
Hello, Dominic. I think it's fine for me. I have Zoom meetings regularly, so.
Yeah. We trust the system, right? By now.
Is sharing, right?
Yeah, Sonia, we can see your screen.
Thanks. Sorry. Perfect.
Great.
I should also get such a fancy background. I have to find if I have to find a good one.
Well, finally, in this case, it's actually completely fitting because I have this Vesida university background all of the time. But now today, finally for this presentation, fits perfectly.
That's true. Okay. Hello, Sonia. I hope it's okay if I use your first name straight away.
Yeah, it's okay. And hi, nice to meet you finally.
Yes, thanks for participating and presenting. It's really great to have you on board.
The invite.
My background always looks so messy here. Okay, let's see how many people come in.
Hello, everybody.
Hello. Hi.
Hello, Jan. Nice to meet you.
Oh, my camera.
Hello, everyone. Hello, Hans-Peter.
Hello. Hi,
Hello,
Dominic.
Sweta. If I may use your first name straight away.
Yes. Yeah.
We did already correct the spelling mistake. I'm very sorry for it.
No, that's okay. Thank you so much. Yeah.
Sure.
Both names are actually correct. So I was, yeah,
Well,
that would, yeah.
You're still happy with us. That's good.
Yeah.
Okay, for you presenters, we will have a short introduction and a few welcome words. And I think you have seen the order of presentation that we came up with. So everybody's prepared, but we still have a little time to relax for people to come in and for the welcome words, and then we will go. I will moderate the discussion, and I will try to keep the short discussion parts to questions of understanding and rather have the broader discussion at the end after we've seen all the presentations, so everybody gets his fair share of time and attention.
Hi, Dominic, Tomer.
Oh,
Oh, hello. Hello, Hiroki. Nice to see you here. Thanks for coming in to the
Very
session.
nice to see you.
Presenters, just before we start, I think I made all of you co-hosts, which means that you can share your screens when it's your turn to present. But if I forgot any of you, please let me know now so we have it already in advance. Dominic, I think you will tell us when to start. Maybe
It's
we
okay.
can wait a few more minutes for maybe a couple more participants, but it's totally up to you. We're already broadcasting on YouTube.
Oh, wow.
Yeah.
That's exciting. So the pressure is on to be entertaining.
Yeah, absolutely.
So now
it's
I have to do the
important
sports
for
commentator
participants.
thing and talk all the time. You know, you mean?
Well, once we officially start, we still have a minute to go. But
Okay.
yeah, from the technical perspective, I think everything is working as expected. So that's all good.
That's wonderful. I think we might wait like 2 or 3 more minutes. It's still shortly before 4 and people will be looking for links and waiting for stuff to load. So
yeah, exactly.
Let's give people a chance to come in, and maybe in 2 minutes we start. Wow, wonderful. Lots of people are coming in. Very exciting. Yes, it's great to see a lot of familiar names and faces. It feels like a conference a little bit. That's very good. So let's wait another minute and then I think we can start. Okay, my clock says it's time to start. Welcome, everyone. I'm very happy to have a very exciting event today. My name is Dominik Wiedenhofer. I'm co-chairing this session together with Tomer Fishman. I'm part of the input-output section of the Industrial Ecology Society, but in another part of me, I'm also a metabolism and MFA researcher. So I thought, why not team up with the metabolism section board and do a joint session, which I'm very much looking forward to. We already here see the program and our esteemed speakers with their various contributions, which come in from an input-output angle or come in from an MFA angle, and I'm really excited to see the crossovers and the inspiration we can get from linking these two research approaches. Before we start, Tomer, do you want to say a few words about the Perpetual Online Conference?
Yeah, thank you very much, Dominic. So as Dominic explained, this is session 9, actually, of our SEM Perpetual Online Conference, which we have been doing throughout the COVID restriction period. And this is our first joint session with another section, with the input-output section, which is very exciting. As you can see here, we have 5 speakers. The numbers apparently are incorrect. They all say number 1 because you're all number 1. But before I give the stage to the chair of the SEM section to say a few words, and I know it's already pretty late in Japan, so thank you, Hiroki, for joining. I want to mention a few things that are expected later. First of all, once this session ends, we will continue in this Zoom link to a happy hour. You may have seen the ISIE announcements about this new happy hour activities that they are organizing and are happening today. And we will continue here. Anyone who wants to stay for a casual chat about input, output, material flow analysis, or anything else, you're very welcome to stay as long as you like to do this happy hour. Let's see how it goes. Beyond that, the session presentations will be available. This is recorded. You may see some notification about that in the corner of your screen at the moment. But if any of the presenters prefer that their presentation is not made available as a recording to watch later, please let us know. Otherwise, we aim to add this session to the increasing collection of recordings of previous sessions of this conference on the YouTube channel of the ISIE. And we usually also remove the discussion and Q&A because, well, it's hard to get permission from all of the Q&A participants to put their contents online. So just to let you know that this is being recorded in order to be available for anyone to watch, not just ISIE members. There will be more sessions of this conference in the next months. And we are going to also announce very soon that this is going to become a crowdsourced effort very soon, where any member of the ISIE are welcome and encouraged to propose their own session proposals, themes, or maybe a full session with speakers and everything already pre-planned, or just a topic, and also to submit abstracts, just like we do to regular old school face-to-face conferences. And we will organize and curate more sessions with the participation of everybody. So there will be an announcement about that coming from the SEM section very soon. This is very exciting. But enough from me. I would like to invite Hiroki Tanikawa, the chair of the SEM section, to say a few words, and then we will start.
Okay, Tomero, thank you very much. I don't have much talking about, but on behalf of all board members of the SEM, I'm really welcome all of you joining here online via Zoom and YouTube. And also I hope all of you being very safe and also well under the very COVID-19 crisis. But thanks to Tomer and Dominic, we have a quite interesting session named The Progress in the Modeling the Socioeconomic Metabolism Combining Material Flow Principles and Input-Output Analysis. So and also as Tomer said, we are during the ISIE monthly happy hour. So I hope everybody being happy to having the lots of idea from our session. Okay, back to Tomer. Thank you very much.
All right, back to Dominic, actually.
Oh, wow, that's a quick one. Thank you very much for the welcome words, Hiroki. I will not keep you all for much longer, just a short note. I will moderate the next 1.5 hours. We will try to have the presentations at around 10 minutes. If you have questions of understandings, please use the raise hand button so I can then call you to ask your questions. And for the broader discussion, let's try to have that at the end so everybody gets his time to present. Okay, so not keeping anyone further, I would like to invite Sonia Kuna to the stage, to invite her to the digital stage, to invite her research on the analysis of the socioeconomic metabolism of nations using pyots from freely available data.
Yeah, hi everyone. I will start sharing the screen for the presentation now then. Which is not going, okay, cool. So you can see the presentation, right? Yeah, okay, cool. So my name is Sonia Cunha, as Dominic said. I'm a PhD student at Instituto Superior Técnico in Lisbon. And in my PhD, I have been developing a method to aid the analysis of socioeconomic metabolism, which should actually be countries and not nations. My bad. And that's what I'll present today. So this work has been developed in the context of sustainable development, so a way to have a better understanding of the socioeconomic metabolism during an economic transition, so we can learn about pathways for sustainable development. The work presented here today has been accepted for publication in the Journal of Industrial Ecology, so you'll be able to read more about it very soon. The goals of the presentation are to present the method to compile the physical input-output tables. I will also go into the features and limitations of the method, how it can be integrated in a methodological framework for the analysis of socioeconomic metabolism, which I will illustrate via a case study for Portugal. So going into the method. The first version of this method was in a paper by Pina et al. On urban metabolism. We have now improved this method. It is now more robust and the results, I believe, are more reliable as we use different assumptions, some other databases, and we have also changed how some of the flows are calculated. The figure on the left shows the overall structure of the results. So the physical input-output tables follow a three-dimensional structure. We have one table for each of the materials, which are 17 categories. And the inter-industry delivery matrix has 37 economic sectors, as it follows the structure of the input-output tables published by OECD, which are also integrated in the model. In white, we have the flows that are first introduced in the tables, which are the known flows, which we can fully define from databases, and those are domestic extraction, imports and exports, which come from Comtrade in the form of products, which we disaggregate in materials using a matrix that does that disaggregation. The remaining flows are either partially defined by databases, or they are the result of the minimization of the difference in the mass balance of the table. So for each table, we perform this minimization, and the result of the minimization are proportionality constants between the materials sold and the value of those materials in the input-output tables from OECD. And in the end, we have a fully defined table. Now, through to the features and limitations. I would also like to refer that we did our best to validate these tables as much as possible, and for that we performed the sensitivity analysis of the results to changes in the databases, and we also tried to validate the homogeneous price assumption for this case. And for that, we looked at the price distribution of the products sold by each sector in Prodcom, and we also looked at this distribution of the sales. On the features, this method is easily replicable. It has been implemented via a Python program, so we can run it for any country or year that is covered by those databases. It can also be applied to other countries. It's a matter of finding alternatives for the data sources. And it also, in the end, because we have a typically structured physical input-output table, any typical analysis done with input-output should be valid. On the limitations, there is the problem of using the homogeneous price assumption. So there are certain less meaningful flows that, as far as we identified, aren't many, that might be slightly distorted, which means that a very detailed analysis into specific flows will require extra care or validation. Also, in such an analysis, if the user has data, he can input that data into the model and improve the results. Also, recycling flows may be misrepresented. Now, on how this method can be integrated for the analysis of socioeconomic metabolism. For that, we propose a four-step methodological framework in which the first two steps are what is already typically done. So on the first one, one would look at the relation between, in this case, domestic material input and gross domestic product. And on the second step, one can analyze what are the materials entering the economy, if there are any changes. The third and the fourth step are the steps which can only be done by compiling the physical input-output tables. So the third one is the analysis of the resource productivity by sector, and the fourth, the analysis of the socioeconomic metabolism, for which we propose the presentation of the illustration, of the monetary input-output tables and physical input-output tables in the form of core diagrams. Now to the case study, which in this case is the Portuguese economy in a period that covers the economic crisis during which Portugal went through a transition. So on the first step that I proposed, we have the evolution of the use of materials by the Portuguese economy versus the economic development in the form of, here presented in the form of GDP per capita. And what we see is that Portugal was going through this somewhat constant evolution of these two variables. Then after 2003, the resource productivity of the economy decreased. So the economy was using more materials for a smaller economic growth. After the 2008, the economy went into a crisis. So the gross domestic product decreased, and so did the use of materials. As the economy recovered, the use of materials increased, but at a slower rate than before. So the resource productivity of the economy overall improved. One of the explanations that has given by literature before for these kind of changes is the hypothesis of substitution. So replacing domestic extraction and national production by imports. In this way, waste would be produced elsewhere. So for that, we looked at the raw material equivalents of imports, here presented in the dotted line on the graph on the right. And we see that the level remained somewhat stable, and that the value for 2017 is very close to the previous values before the economic crisis. Now looking, so what we learned from this is that the economy changed and we had an improved resource productivity. The second one, the second step, we see that right away that the most meaningful material flow in the Portuguese economy is stone and sand, so non-metallic minerals. And we see that there was a big decrease in the use of that material during the crisis, and that as the economy recovered, it increased slightly, but not to the previous values. We can also see that not all materials reacted in the same way to the crisis. So unlike fossil fuels that showed a slight decrease, biomass stayed somewhat constant, and it has increased to values higher than the previous ones, unlike non-metallic minerals. The third step, which is a productivity by sector. We looked at productivity by sector, which is given by value added over the total inputs in the sector, which are domestic extraction and the imports, which we already knew, and the total acquisitions from other sectors, which are given in the physical input-output table. And what we saw from all of these was that the productivity of the economy increased from an increased value added in the service sector and a decrease of materials in the construction sector and associated sectors, which we learned that they are associated on the fourth step, where we look at these very complex graphs with a lot of information, which I'll try to explain. So here we have the case for 2017, and starting on the right in the physical input-output representation, here we see that the major material flows entering the economy enter through domestic extraction. They go into mining of non-metallic minerals, and then those are mostly going into other non-metallic minerals or construction. The ones that go into other non-metallic minerals also go to construction, whose output then either stays as fixed capital of the sector, flows through the sector as well, or is sold to services. Now, to look at services, one is better served by looking at the monetary flows, as the sector doesn't have physical output. And we see that the services, the activity will satisfy mostly the demand of households, so household final consumption expenditure, followed by the sector itself, and then it goes into either general government or exports. Now, looking at the evolution of these graphs through these key years, what we see is that during the recession, the construction sector decreased a lot. So it went from a value of almost 40 on total, so inputs and outputs, so it would only be half for the inputs, to a value of under 20. And then as the economy recovered, that value stayed below the previous one. On the other hand, if we look at services, the sector did improve and surpass its previous values. However, its demand for construction stayed below the values previously measured. And I'm over time, I'm sorry. Quickly finishing. So what we learned from this is that we can now, with the currently collected data, compile physical input-output tables. These results can be used to analyze the socioeconomic metabolism of a country and learn from that. And this work is also now being used to study the role of key sectors in economic development, and also for a comparative analysis of different countries and how they reacted to the economic crisis. And that's all. I would like to take the questions now, if you have any.
Thank you very much, firstly, for this very exciting presentation. Great work.
Thanks.
Do we have any immediate questions? Either you can use the raise hand button, or the first brave person can just speak directly, as there is no queue yet. So who would like to have something clarified or a follow-up question?
We have Jan, I believe.
Yes. Oh, my screen is jumping around. Yes,
actually, I was just clapping hands, but I can as well ask a question. Did you use the Leontief IO model to calculate the monetary tables?
So it follows the Leontief model. What I haven't done yet is to use its ability of modeling changes, for example. So change the demand and see what happens to the inputs in the model. But it should work. Like, the model follows the typical structure, so it should work. And sorry for putting on the spot. I thought it was a raised hand.
No worries. Any other questions at this point? Otherwise, I think it was a wonderful and very clear presentation. There is a question in the chat. Do you convert via import prices? Did you convert via import prices? I guess this refers to the Comtrade and other trade data you have in there.
So I used the Comtrade data, which has data in monetary units and physical units. Some of the physical units are missing, as anyone who uses the database has noticed. And so I estimate that using the methods also used by other authors. So they should be okay.
Okay, we have a question about a broken microphone, so I will read it out. Will you publish your pilot tables for use by others?
So as part of the publication in the Journal of Industrial Ecology, these physical input-output tables for those 3 years for Portugal, they will be published. And I have also produced for other countries. If anyone needs them, I'm happy to share. But as of now, there's no plan to actually make them, all of them, available.
Okay, so a great opportunity for collaboration, actually. Okay, thank you all very much. Let's move on so we have enough time. Thank you, Sonia. Now I would like to invite Hans-Peter Wieland to the stage, to the digital stage. He will tell us about building global physical input-output tables in a virtual laboratory. Laboratory always sounds exciting as a scientist.
Sounds scientific, yes. Yeah.
Please, go ahead.
Wait, I have to share my screen. Sorry, I have 3 screens here. Makes it a little bit more complicated. Bildschirm freigeben. Yep, here we are. Do you see my screen, right?
Yes, please go to presenters mode also, and then we are,
sorry.
yes, wonderful.
So,
oh, that was one click too many.
I think now you see my first slide, right?
Yes, yes.
Okay, thank you.
Wonderful.
I take the time too, so that I don't speak too long. So, yeah, first, hello everybody, hello world, hello internet land. Thanks for having me. I'm going to talk about my world, the PioLab, and how I'm building global physical input-output tables in a virtual laboratory. And I'm doing this, making the case, using the case of global iron and steel PIOTs. The PioLab is part of the FinePrint project. You can see the very nice logo here on top, which is a big project that is mainly concerned with fine-scale environmental impact assessment of mining activities on the subnational level, basically, and then to investigate the consumption drivers of these mining impacts. So basically there is one input-output model or PIOT in the center, and then we have a satellite count with different impacts and pressures coming from mining. But I'm not going to talk about this now. I'm just going to talk about the PioLab, and in the end of my presentation, I will tell you, what is coming next. So basically, I think I'm going to start like this, taking stock of input-output modeling. What are the challenges? And Sonia already mentioned some of these challenges. Well, first of all, the raw data is pretty scarce, incomplete, and conflicting. We have different data sources which tell us different things, which makes it quite difficult. Secondly, we're having different classifications, which where it is not always clear what is actually meant by these classifications. And thirdly, from my point of view, the most important point here are the uncertainties of all our data sources, which are usually unknown and probably are pretty high, especially when we are working with physical data. So the bottom line here is that building input-output models, being physical or monetary, is a time-consuming and very complex task. So this is the situation. And I was happy, I was lucky to visiting Manfred Lenzen and colleagues at the University of Sydney, where I have learned to work with one of their things that they are doing there, which is the Industrial Ecology Virtual Laboratory, or just the lab, basically. There are different laboratories out there. There is one laboratory for China, Indonesia, Taiwan, United States, Japan, a global MRIO laboratory and things like this. But all these laboratories have some common features. But the first pillar is that we're having a generalized raw data management system, which streamlines the way in which we are pre-processing our source data in order to make use of it for our modeling. And this is actually done by mapping the source data to the so-called root classification, which you can imagine is a very detailed list of products, sectors, flows, processes, and regions, which always is an aggregate of my source data. So it always matches my root classification. The second pillar is ISIE, which is a one-step reconciliation engine, and ISIE is in its core a constraint optimization tool, similar or like KRAS, and ISIE allows us to formulate constraints for different elements of our metric. So not only the column and row sums, but also some ratios of different flows or some elements within these tables. And ISIE also allows us to finding some compromises for situations where our data sources are in conflict by tagging all our data points with uncertainties, which we have to define. The third pillar of every laboratory is a high performance machine in order to be able to reconcile the different data sources in a reasonable amount of time. The bottom line here is, or the philosophy is, there is not the one multi-regional model input-output table that will answer all our different questions. So the idea is, I think, to be able to compile input-output models that fit specific research questions that are tailored to some specific questions. And this whole laboratory, the purpose is to make this easier so that we can reuse all these data sources more easily. Well, I have basically built the first physical laboratory here, which makes a prototype for the global iron and steel supply chains, the root classification, which works as a repository of all my raw data, differentiates 221 regions, 76 processes, and 266 flows. The tables that I'm building, so the base tables, the base classification of the final table has 32 regions, 30 processes, and 39 flows. Of these 32 regions, 5 regions are rest of the world, and the other regions are just countries. And these 72 countries, they account for more than 90% of iron ore and steel production and consumption. So I think we have the hotspot countries contained in this model. So the whole, as I've mentioned, so raw data is pretty scarce. So the idea here is now in the PyLab, then whenever we cannot find valid or trustworthy primary data, we're gonna stick to modeling results of other methods that are usually used in industrial ecology, like dynamic MFA for estimating the end of life scrap, LCA for detailing some processes, or some waste input-output modeling. So I'm basically making use of all such different sources. So it's a big patchwork, and here I show you just quickly a list what we are having here. So the word steel data source for steel production of different steel products. We have BARGI, trade data, UNEP, IRP data set for iron ore extraction and grades, energy balances, end of life scrap from Stefan Pauliuk's model or paper, Exile-based 3 for the waste input-output modeling, and some LCA. And so there are plenty of different sources that we are integrating here. We are tagging all these sources with an uncertainty and making an initial estimate of this table. And then we basically load it into ISIE, or we try to reconcile all these data sources. The tables that we are getting out of this, so the general framework of these multi-regional physical suits, you can see it here. It's an example for 2 regions. We have, of course, here the use tables, which are flow by processes. We have the supply table, which are processes by flows. We have the final use table here, which would for stock building materials, so like steel that is going into a car, into use or buildings, you would found that steel here. And we are having here boundary input and output blocks. So these are these blue greenish tables here. So inputs from nature is pretty clear. So this is everything that comes from nature, which is not processed by human activity. So mainly the crude ore and air. But we are also, for making steel, you actually need more than iron ore. You need coke, you need limestone. And some of these things, some of these flows are actually produced by society. And these inputs would then be found here in these SEM inputs, boundary inputs from SEM. Or otherwise some byproducts that might be used for construction too, like the steel slag or something like that, is also used for other societal activities. And output to nature would be, of course, the greenhouse gases. So with this framework, we basically have a model core system in yellow, and we have the background system. What is the time? Am I already too long? Unbelievable.
Yes, okay. Please try to wrap it up.
Okay, I wrap it up. I'm just, how did that happen? Okay. Anyway, I wrap it up. So this input output here show you the use table, which basically looks like this. So it's a pretty sparse matrix, but you could also look at the input output tables in this way. A Sankey diagram, and yeah, basically there are different ways of looking at it, and I'm skipping here a couple of slides, but you could also use these physical tables to calculate some basic economy-wide MFA indicators, domestic extraction, DMC, and RNC. The facilitators asked me to to comment on some insights from combining input, output, and SEM. And the first word, the first sentence that came to my mind was slicing up the social metabolism with physical input, output techniques. So this is what I have in mind, actually. It would be a good title for my PhD, I think. On the one hand, the social metabolism, which is a holistic concept, right? It's the totality of all the biophysical flows, processes, structures, basis, whatever. But on the other side, we have these input-output techniques, and I'm talking here about the most basic understanding. So the mathematical formalism, generalized modeling rules, which is independent of units, basically. So there is a wealth of techniques that can be used to operationalize the social metabolism. So could be integration framework for other methods too. The drawback of here is basically the cross-fertilization of different methods and concepts can be quite challenging, as it may lead to great confusion. Yeah, so this is diplomatically put here. The outlook, I'm done now, I'm just 2 minutes over the time. I'm going to present at Industrial Ecology Day, which happens in 3 weeks or something, the next version of this PyroLab, which is going to be spatially explicit, and it will be a holistic modeling framework for materials and energy flows, which extends what I just talked about with impact assessment for mining activities. And yeah, basically this will then be my work for the next year. Sorry to talking too long. Thank you.
Thank you very much, Hans-Peter. Very exciting work also. Great work for further analysis. And I do hope that this session actually adds to the clarity and not to the confusion when cross-fertilizing. So are there any immediate questions that people would have like to answer? We don't have a queue yet, so you can also just speak out.
Can I ask one question?
Yes, please, go ahead.
Yeah, I was wondering about indirect impacts and the way they were calculated using this approach. So indirect consumption in steel industry, it was calculated directly from input-output table and some material intensity coefficient, like multiplied by, in order to separate indirect flows from total. Or does it, because I didn't find this information, I was curious, does this problem have been approached?
I'm not 100% sure if I understood your question correctly. We can always get in contact afterwards. I think we once had contact per email or something like that. But I think, yeah, this direct flows, many of them are just estimated by using some input flow or output flow, which might be the use of peak iron in one region. Multiplied with some factors that I'm sourcing from the LCAs or from different other steel industry sources, how much steel can you actually make out of 1 ton pig iron? How much greenhouse gases are associated with this? So these are very crude initial estimates, which we then try to reconcile and balance in the end. But I don't know if I have answered your question. We can get in contact afterwards.
Yes, maybe you can take that also to the happy hour for a more detailed technical discussion. Let's maybe have the questions asked in the chat shortly. Hans-Peter, how was uncertainty calculated? And the second question is if there is some kind of standard data input structure to use the PioLab for other regions, countries. Maybe you can very quickly answer these two questions.
Very quickly, okay. The uncertainties, I just refer here to that slide because I ran out of time. This rocket plot basically shows you on the x-axis the reported values, how they are in our source data, and on this y-axis the values that are realized in our final table. And as you can see, this is a rocket here, so it gets sharper and sharper to the top. We basically use this law of large numbers, where we assume a very large number, such as steel production in China amounts to 500 megatons. The relative uncertainty of this might be smaller, let's say 15 to 20%, but maybe welded tubes traded between Malta and Greece, or I don't know, of a ton 0.5, could be a ton 0.5, could be 100 tons, could be 1,000 tons. I don't know. So this is basically what this rocket plot shows. So these are some strong heroic assumptions, or maybe not, I don't know. But that's how we estimated the uncertainties. The other question, I think the number of regions is can be adjusted depending on your research questions. I cannot remember exactly the question. So
the question was about transferring that approach to other countries. And I think that's the point of the IE lab, to actually be able to do that.
Yeah, of course, other countries. Like in theory, you could build now iron steel piers for all countries of the world. In theory, in practically not. But, okay, so.
Okay, that's a bit of a depressing answer, but
yeah,
I think in practice you probably can, but I think the data requirements
can with a lot
high.
of time and a lot of motivation.
Okay, so sorry, Helmut, I have to move on now. There is a question about log spaces and uncertainties, but maybe let's not get stuck in technicalities right now. Thank you very much, Hans-Peter. Very exciting work. I'm sure people will get in touch with some more questions at some point. And right then, I would like to move on and invite Sweta Singh to the stage. I'm sorry about pronunciation issues. You're still muted. And we have a screen share starting. Wonderful. Yes, we see the screen. It looks good. Okay, you have to unmute yourself.
Yeah, can you hear me now?
Wonderful.
Okay. Yeah.
Please, the floor is yours.
Okay, thank you. So thank you very much. And so thanks for the wonderful leeway into physical input-output tables. And we saw some good examples. What I would like to talk about is how we can standardize the approach for physical input-output table, and taking more of a bottom-up approach, talking about mechanistic engineering models and integrating them into input-output framework. And most of the work that I'll talk about is based on my PhD student work, Gargia Vanova, who just recently graduated in December. So I wish he could give the talk. So physical input-output tables, as we know, are a very good standardized frameworks to track material flows. And the idea is that using the input-output framework, we can see how different industries are interacting in terms of material flows and which commodities are being used for imports, exports, or the consumption. But one of the most strength of the physical input-output table is also tracking the waste and the residuals used and the residual production in different regions. And the idea is that if we have this structured framework, we can map the biophysical economy. And if we have the transparent insight into how different systems are interacting in terms of material flows, we can also restructure the economy towards circular economy or minimization of waste. So to begin, where we began our work was on a very sub-regional scale. So we were more interested in the regional physical input-output tables, because most of the decisions about restructuring of any economy happens at the local scale. And from that aspect, what the work began was we were looking at the empirical data, and we began with the state of Illinois in the United States to understand how the agro-based economic sectors were interacting in the terms of material flows. So this was a very empirically derived model, and we could track only 22 sectors. And the basis of selecting those 22 sectors was the major agricultural commodities in the region of Illinois, which is a very heavily agro-based economy. So using that, we looked at this complex interaction. So what you see here is the physical input-output table for the year of 2012. But most importantly, the challenges we found was that this was a very slow development of models. So this work actually started in 2012 when I started my postdoc, and it took us about 2 years to get the data and get the structure of the economy mapped well. And then if we wanted to reproduce the model for other regions or other year, that was not feasible because some of the data, as some of the previous speakers have mentioned, is missing in the reported values. And also, if another important question that we wanted to understand is that if we change anything in one particular economic sector on the physical level, how does it cascade into the whole economy? So all these questions, when we were doing with the empirical understanding, was not feasible to address very easily without making very strong assumptions. So to overcome these challenges of empirically based physical input-output table, what we propose is to move more toward the mechanistic approach, where what we are saying is that we can integrate different mechanistic engineering models. So on the left, you can see the mechanistic simulation model. So we can have simulation models for each of the economic sectors based on the understanding how these are taking in different commodities and resources and transforming into the useful commodities that flows to the whole economy, and then build an algorithm that takes this simulation output to map the industrial network, or what we call as the physical input-output table for the economic sectors. So I'll now talk about the algorithm and what's the rationale behind taking this approach. So our approach basically was motivated to make it the reproducibility and adaptability much easier, and it definitely takes lesser time. So we developed new physical input-output table using this approach, and based on the 2-year data, when we had the model, it could take us months or even days for someone to reproduce the same model. And also, as the new technologies come in, we can replace one of the sector with the new technological development that can update the whole interaction of different commodities that is state. So it can automate the updating of the physical input-output structure. So that's the whole proposed solution that we took for moving away from the empirically based approach. And the rationale is that when we look at the economic sectors in the input-output table, based on their operations, we can talk about homogeneous sectors and heterogeneous sectors. So homogeneous sectors are the sectors that have very similar technological operations across different regions and across different years. So for example, some of the sectors like soybean and oilseed processing and other energy sectors can have the capital, infrastructure, and technology logged in. So for multiple years, we can use the same models to process different material flows. So using that classification of homogeneous sectors, we can have a standardized engineering-based model that uses the mechanistic relationship based on chemistry and physics of the processing of different resources to get to the commodity balances for that particular industry or sector in the region. And then if we have an update in the technology, we can easily update that particular representation of the sector in the economy. Other type of sectors that we look at are the heterogeneous sectors, and these are more which vary based on the scale of operation, based on the region and year. So one example is the cattle ranching and farming. And since it is very much operational scale developed, so what we propose here is that we can have customized model based on the biological information of how these different sectors operate on different inputs, and can have those variables to reflect the local setting. So this is more challenging because then after we classify into homogeneous and heterogeneous, for homogeneous, we can have one type of model that can be used for multiple years and multiple regions. But for heterogeneous, that every user has to update the model as per the reflection of the local system that you are doing. So then the algorithm, what it takes is that we start with the sector identification and classification. The sectors are mapped to the NAICS code at the finest scale. And then we classify it into homogeneous or heterogeneous. That gives us an idea of what kind of engineering model we need to develop. The key step here is to develop the engineering model and actually validate and scale to reflect the economy that we are modeling. Once we have that engineering model developed, then we do the data extraction from the simulations and organize it into physical supply and use table. If we have import and export data on the final consumption for the commodity that we are looking at, we add that data and then do the mass balancing. So the mass balancing is the most important part. In the beginning, we get imbalanced physical supply use table and we check for the sectors. If there is imbalance, that means that some of the engineering models are not capturing some of the physical flows. So we go back and fix the engineering models to identify if any error has been made in modeling the sector. Once that's updated and we have industry level balance that maps the input and output, that mass balances, because the thermodynamic mass balance has to be maintained. Then we also include the import, export, and final consumption data, and then we look at the commodity level balance. And if for a region we find that the commodities are not balanced on the input and output side and the supply and use tables, then we add a rest of the economy's column to actually account for that, because the idea is that some of the commodities may be coming from other sectors that we have not yet modeled. So that rest of the economy model captures it and we just allocate it to rest of the economy. And then we check the rest of the economy industry balance. And if that's not balanced, then we also add a slack variable to account for any missing. So all the uncertainties, then we know where exactly those uncertainties have been captured that can be iteratively updated. And then at the end, we get the balanced physical supply use table. Once we have the balanced PSUT, we use the standard Eurostat metrics. In this case, we have used the model D that matched our assumption of tracking the commodities, and then convert into PIOT and check for mass balance. So that's the whole algorithmic overview. And to talk about how the data extraction works, so in the central box, you can see the engineering model prototype. So in any of the engineering model, you have different subsystems that are processing different commodities. So the input side gives us the data that goes into the physical use table, which is the commodity by industry. And the output side of each engineering model gives us data for physical supply table, which is the different industry giving different commodities. We also have the waste, so it can be GHG emissions, but also solid waste and liquid waste that is coming out of any economic sectors. So in this way, we have a complete mapping of all the sectors that are based on very mechanistic simulations, and the mass balances are already taken care of. So the scaling part is very important because that reflects what was the scale at which that material flow was happening in a particular region in a particular year. So I will talk about the scaling part through an example. So what we did was we used this approach to, again, model the agro-based sectors. And since it's a bottom-up approach, we are limiting just for the testing of the approach for 10 sectors. And you can see that for some of the sectors, we had to develop a Python-based model for plant growth that accounts for all the mechanisms of plant growth based on the weather variables and based on the inputs. For the hog farming, which is again a heterogeneous sector, we had to look at an animal growth model that accounts for how the animal grows based on the feed inputs and gives us the input and output for that particular sector. The sectors 7 to 10 are more standardized homogeneous sectors, which are manufacturing sectors, and that could be represented as the Aspen Plus models. So once we had this classification and the models developed, we wanted to scale it for the region. So the scaling happens by selecting a scaling variable, which could be an input or output. So for some sectors, we know how much of the fertilizer consumption or the, let's say, the biomass consumption is happening for that particular region. Based on that, we scale the engineering models to reflect the operation of that sector in the region. And we select an output variables to validate the model. So the output variables could be soybean yield, some of the things that are publicly tracked, or the soybean oil and things like that. So any output that we have. And for then we validate it and we look at the error percentage. So obviously it's not perfect. We do have error percentage, but we know which of the sectors have how much error in reporting the mass balances, or how much is the error in that particular model representing for that sector. So in future, when we want to improve on our models, we can go back and improve and match it to the validation sources. So this is the key step. Once we have this done, then we just input it into the algorithm and extract data for physical supply use table for different commodities, and then convert it into physical input output table. So this is the example. So this is the physical use table shown as the Sankey diagram. So we have different commodities going to different industries, and we get a very detailed automated mapping from the engineering model simulation. Similarly, we get the physical supply table. So where we get all the commodities that are provided by different industries. So this is an industry by commodity table that is shown as Sankey diagram. We also get a very detailed map of different waste being produced by different industries. So I'm not showing the quantitative data here just for making it not look very cumbersome. Then for the PIOT, we can look at the physical input output table as heat map. So this is just showing how different industries in the Illinois region were interacting with each other. And this is again based on the EM simulations and then converted into the PIOT models. So I'm not going into the quantitative values right now, but you can see the intensity of different industrial sector interactions. So corn farming is interacting very high with dry corn milling, and also with the hog farming, because there's a lot of interaction with the hog farm that is consuming corn for that particular region. Another strength was that we could introduce a recycling sector in the economy, modeled as an engineering model simulation. So we had an Aspen model for the new recycling technology. And we could then introduce it and read on our simulations to look how the interactions would change. So the hog farming had a lot of waste that went into the recycling, and that updated how the different fertilizer sector was interacting with sector. So we can see changes in the intensity of interaction of different sectors based on the material flows that are recycled. So in summary, what we are moving towards is looking at more reproducibility and fast generation via cloud-based platform. So we are developing this collaborative cloud platform, and I do have a longer video on how this tool works. So the idea is that each user can upload their models, and we also provide some of the default models for the sectors. And once they upload the validated and scaled models, in the back end, the Aspen models and Python services run, and we can then get an Excel sheet of PSUTs and physical input output tables. So this will be available through the MyGeo Hub, which is a cloud platform service from Purdue University. And we are hoping to test it internally right now and then make it available to IE community and other researchers for use. So the hope is that it will be more collaborative. People will be submitting their models and results, and it will be available for everyone. If users do want to make their models private, that functionality we are adding, because there's some, unless you want to publish and then make it available. So that is also available. So ongoing in future work, I think the most challenging task is the developing EMs for the heterogeneous sectors and validating it. And we did make an assumption of steady state for a lot of industrial operations, which we want to update the algorithm to move towards more stocks and the accumulation in the industry. Some of the sectors in the economy have bypassing material flow. So we still want to think how to map their interaction with the material flow sectors. And internally, we are beta testing this PIOT hub and will soon be releasing. And I do have a video that I'll upload very soon for public view. And obviously, the most important point is that it has to be very collaborative, because mapping the whole economy bottom up is a very big task, and it will require a lot of researchers to test and validate and kind of cross-validate the models that have been developed. With that, I would like to thank NRC postdoc, where I started the PIOT work, and then the most recent National Science Foundation funding that has provided funding for this algorithm development. My students, especially Dr. Gargia Vinnova, who's now with Amazon, and he did most of the work in developing the algorithm and the backend Python code, and Jaevu Shin in computer science department, who implemented it in the cloud platform. And I'd like to end there. Thank you all and take questions.
Thank you very much. Great presentation. Really excited to see PIOTs independently estimated without using the monetary input-output tables as a proxy. I think that's really important to take this route also. Are there any immediate questions from the audience? I think there is a lot to grapple with and to look at in detail, especially the collaborative part. Rick, I have a hand from Rick, and nice to see you.
Hello.
Here.
Hi, everyone.
Please, go ahead.
Yeah, thanks for the presentation. It was really, really interesting. I was just wondering about your example of adding the recycling sector. I couldn't quite see what you were modeling there, what was being held constant and what was then, what the predictions were, if that makes sense. Could you explain a little bit about how that works?
Yeah, I did not go into detail. So for recycling sector, what we did was we looked at the default physical input-output table that was generated and looked at the waste, and we identified the waste to be from hog manure. That was the maximum waste in that region. So we introduced a recycling technology to convert it into fertilizer and also recycle some of the waste water, and then reintroduce that as a recycling sector in the input-output model. So what that did was that updated all the commodity interactions and how much the sector needed from other sectors. So that's how it was done mostly.
So it mostly affects your rest of the economy flows, I guess.
Yes. So so the balancing was again done for the whole region again, and looked at how the material flow intensity changed. So we do have a paper in review right now on this work, and it should be soon out in a month.
Great. Thank you.
Thank you very much. We have a question in the chat from Edgar, and he's wondering how the model is mechanistic because your data is empirical, so the model is empirically driven. And what do you mean with the mechanistic part there?
Oh, so data is empirical only in sense of scaling the model, but the model is mechanistic in the sense that each of the sector is operating some technology. So for example, the soybean oilseed processing has all the transesterification and different chemical processes that are underlying. So we model the mechanism of transformation of different commodity into products and waste first, so that stoichiometry is accounted for. And then it is scaled to operate at a regional scale. So if a region is saying that they are operating at 1,000 tons per hour for processing of a soybean, then we take that into account to scale the variable model. And then for a year, then we account how much that would lead into the material flows. So I don't know if that helps.
Yes, you got an okay thanks in the chat. Thank you very much. Any other? Yes, we have another question. Joanne, please go ahead.
Yes. Hi, Shada. Thank you for the presentation. Actually, my question is kind of related to Edgar. So when you run the Aspen Plus simulation, basically your mass and energy balance largely driven by the operational condition information you put in, the process design information you put in. So even like say, if we look at the chemical sector, for the same chemical, just change the process design a little bit, the whole mass balance will be changed. Yes. So how that large part of uncertainty took into consideration when we use the result of Aspen Plus?
No, that's exactly the point, Yuan, that once the technology changes, your mass flow can change. So since we have built in that in the algorithm, so if you change the technology, the whole physical input-output table can automatically get updated. So the idea is that for a particular region, and we did a lot of research and talking with industries, that once the technology is locked in for a long time, it does not change much for the only thing that uncertainty happens is in the way the steam consumption or anything else based on the operational variable changes. So the mass balance, so if you have 100 tons coming in and it's operating at that scale, it will continue to be unless the plant is shut down. So this is accounting for the continuity of the plants as well. So that uncertainty that you are talking about will only occur if the technology is changing or there's some significant change happening in the economic sector. So we actually talked to a lot of the wet corn processing milling sectors here. And what they said is that each of the technology is being designed by the same company, and there's a lot of homogeneity across different regions on how this processing is happening.
Yeah, I have this question because I have a project like with pulp and paper industry. They have the same facility, but they switch on what product they do. So same for the chemical plant, their facility is the same, but the product they produce and operational condition can always be adjusted because every year they want to plan to maximize their revenue.
Yes, and that's exactly the good part is, right? So if you know that there is a change happening in the economy due to the technological operations change, you can reflect it in the engineering model, and then your input-output table will get updated. So the algorithm is pretty robust in accounting for that. So the input model has to really be the reflection of what's happening in the economy. So you're right, we can count. So that's where the strength is, that we can account for that uncertainty by updating the models as we want. So think of it as more as scenario modeling, right? We can update the models to reflect those different scenarios of production.
Okay, wonderful.
Thank you.
Welcome.
We have some reflections in the chat also. There is also a short question about validation. Maybe you can very quickly answer it so we can then move on to the next presenter with lots of good questions, but not enough time. So please, a quick answer on validation with empirical data.
So validation was more of seeing that the models that we developed and after scaling, how closely it is mapping the publicly available data on the output side or any other variable. And that was more to just for us to be very confident that this model after scaling is reflective of the economic or the economy processing the materials. So even if you don't validate and you have fair amount of confidence in the model, the algorithm works, but validation just gives us a much more confidence that we are actually capturing what's happening in the economy for that particular year.
Okay, thank you very much. We do have to move on. There might be time afterwards to continue discussions. Thank you very much for the presentations. And next, we are moving a little bit more into the MFA world, maybe. So I would like to call Jan Streeck to the floor.
Yes, hello, everybody. Let me just share my screen. So I hope you can hear me clearly.
Yes, we can hear you and your slides are working. Please go ahead.
All right. Thanks, Dominic. Yeah, hello, everyone. I'm happy to present our ongoing work on dynamic material flow analysis, or MFA, and how we might use input-output analysis to find out where materials end up in which end uses or products. And dynamic MFA is a rapidly evolving approach that can calculate stocks and flows at different scales and also for long time spans, and thereby inform important concepts like the circular economy or the resource climate nexus. And MFA models are often distinguished into stock-driven and inflow-driven MFA models, the majority of recent studies being inflow-driven models. And many of these use statistics on aggregate material consumption, and these flows together with a lifetime model can then be used to calculate material stocks. And one major challenge of this approach is the differentiation of material end uses, or in which types of products or sectors these materials end up. And therefore, our ongoing work wants to work towards a method that can differentiate these end uses, that is time dynamic, consistent, and robust. And in order to illustrate a little bit better what we mean by this term end use, I brought a very simplified MFA scheme. So let's just assume that we have data on aggregate total steel consumption, which enters a process of manufacturing and comes out as final steel, which we then, with a lifetime model, can use to calculate aggregate steel stocks. Now, while this is already nice, we can model stocks and flows. It would actually be much more informative if we could say in which end uses the steel ends up. So for instance, in buildings or transport or infrastructure. And in order to do that, we need kind of a split or a ratio in order to split the total steel consumption to these end uses. And in here, we call that end use split. In the literature, it also has been termed a little bit differently, like for instance, branching ratio or sector split. And in many studies, inflow-driven MFA studies in the literature, you can see that they use data on so-called industry shipments, which is data in physical units, which basically tells us, for instance, how much steel is going to the car manufacturing industry versus to the construction industry. And these data can then be mapped to the desired end-use categories, for instance, buildings or transport, in the MFA studies. And this has been done a lot, although there are quite some limitations to this data source. It is extremely scarce. Sometimes you even have to pay for it. And oftentimes you actually don't know how much of the total material consumption is covered by the data. So this data might be helpful if you focus on a material or country that has a lot of data available. But on the global scale, we saw that often these data had to be extrapolated in time and space. So if you want to move towards covering many countries and materials, it would be really great if we had more accessible and comprehensive data sources. And here is where input-output tables with their sectoral resolution might be potentially useful. So that's why we asked ourselves in the literature, which methods are used up to now to derive these material end uses for inflow-driven MFA. So we started a literature review and to compare these concepts on a theoretical basis. And secondly, we applied these methods to the USA as a data-rich case study to check the comparability of the results. And I'm now coming to the conceptual comparison. So we already saw that the industry shipments in physical units can be helpful, but come with many limitations. And therefore, the monetary input-output tables might also be useful to calculate the end-use splits, which require assumptions or modeling of the relation of monetary and physical flows. And in the literature, we identified 4 distinct methods to calculate these end-use splits. Unfortunately, I don't have time to go into the very details here, so I just want to give some key distinctions of the methods. So first of all, there's what we call the Gauche type method, which has been used, for instance, by these 2 studies. And this method only uses part of the input-output table, the inter-industry transaction matrix, and thereby calculate so-called market shares, which can tell us how the output of an industry is distributed to other industries. And with this, we can calculate end uses in the end. And then the second type is the Leontief type models, which also use the final demand matrix and thereby can calculate how much material input is required to the different final demand categories. And below this concept, we found 3 sub-approaches, which basically differ in the way that they manipulate the monetary input-output tables. So the first one is the consumption-based approach, which basically just uses the input-output tables as they are. The second one is the YOMFA or waste input-output approach, which tries to introduce kind of a physical logic into the monetary input-output tables by, for instance, deleting flows that are assumed to be services rather than physical flows. And the last one is a variation of this, which basically allows for assigning different prices to the output of one industry sector, depending on to which sector it is outputted. So far regarding the conceptual comparison, and I also brought some examples on the application of these methods. So for some materials and end users, we saw that it can work quite well. For instance, I brought you the example of aluminum going to construction. In red, you can see the physical industry shipment data, and the dots are the input-output derived results. And while there's not really a perfect fit, you can see that it doesn't deviate too much. For other materials like copper, for instance, we see actually diverging trends of the physical and input-output data sources. So that doesn't work that well here. One more point that you might criticize is, well, you have an end use on the level of construction is really broad. So the US input-output tables are actually much more detailed. So you can also go further into more sectoral or end-use resolution. For instance, here illustrated for cement, going to residential and non-residential structures and transport infrastructure. For the residential, you can see that works quite well, while for transport, not that well. And you can even go potentially further into detail, disaggregating the residential sector into single family and multi-family houses. And you can see that it also doesn't work that well here. So you might wonder if there's a kind of a trade-off between end-use resolution and accuracy. So far regarding some examples for the application. Now coming to the discussion or conclusions. So yeah, in our work, we found some opportunities and challenges of combining these methods. First of all, as already the other speakers pointed out, of course, input-output analysis is useful for introducing the end-use resolution to the material flows. However, in the course, some decisions and assumptions have to be made, which really make us wonder how safe it is to just use the methods, the input-output methods, when you don't have any other data sources available to cross-check. The methods that I presented also come with certain advantages and disadvantages. The waste input-output method might be best suited as it incorporates principles from both worlds, MFA and input-output. However, for instance, the Gauche-type method doesn't really require a lot of input-output knowledge. So it might be really handy for MFA practitioners that are not too familiar with input-output analysis. And last but not least, also the system boundaries of both approaches have been a bit challenging in the course. Now coming to my last slide, just what I'm going to do with these results now. So this is still ongoing work. We want to complete it. And here, I want to ask your crowdsource your knowledge, basically. So if you know of more approaches or relevant papers, I'm happy to get messages in the chat, or please speak up. And after completing this work, we would like to apply that to the material flows of the US, and potentially, hopefully, also to an MRIO to kind of spread that to the globe. And with this, I'm done. Thank you for listening. And yeah, questions, discussion.
Thank you very much. Great presentation. Thank you very much for nearly perfectly staying on time. That's always good as a session chair. Do we have some immediate questions? Please feel free. The first one can directly speak up. Everyone else is invited to use the raise hand button. I do see some claps from our participants. So you get some praise, which is always good.
Yeah, maybe I can just reiterate my question also, if you know of other approaches. For instance, I saw some papers on absorbing Markov chains. I didn't really look into that yet, but if you know of similar approaches, please.
Okay. Any questions from the audience? We are also invited to use the chat if you have any suggestions or questions. I'm happy to read out questions. Maybe too much complexity at once, so many different methods to compare and understand. Yes, Rick likes the comparison of different methods. There is a quick question from Z. To what extent do you think the price heterogeneity would affect your results?
Yeah, thanks for the comments, and thanks, Z. As you saw, also you were cited here. So one of your papers was a good inspiration. Yeah, I think that's, I didn't really look into that very detailed yet, but I think that might play out quite important for different materials. So for instance, these methods seem to work quite well for aluminum, which also has been a great subject for studies. So many studies on this have been published. And then if you look at commodities like steel, imagining this going to automotive or construction industry, the price difference might, of course, make a bigger change here. Or also for wood, there's indication, for instance, if you have wood going to furniture, which might be more expensive, that this might bias the results. So we have to see how this plays out. And it would be great to do something like Sonia did, for instance, looking at the price variability, but we are still kind of, that's the next step, or the step after even. Thanks.
Okay, thank you very much. Good suggestions for some next steps. That's always very helpful. So if there are no other urgent questions at this point, it seems like I would like to invite our last presenter of today's special session, Christoph Helbig, to the floor. Wonderful. Yes, your slide is working perfectly.
And now I'm muted as well. Thank you very much for this kind of introduction. Good morning, good afternoon, and good evening, wherever you are. It's my pleasure to introduce Matrace Multi to you, a model which Yasushi Kondo and Shinichiro Nakamura have developed together with me from Waseda University. So also thanks to Japan Society for Promotion of Science for funding this research project. And also thanks to Jan for mentioning a lot of the terms that are coming up now again, some of the methodologies as well as the basic idea and goals of a dynamic material flow analysis. Because Matrace Multi, where we try to simultaneously trace the fate of metals, is doing exactly that. It's a dynamic material flow analysis model. What is the basic goal? What we would like to do with Matrace Multi as a model? We're tracing the fate of metals in the global planetary economy throughout recycling. We do that because we want to know to what extent metals are dissipated, that means being unrecoverable or not available for recovery in the future, through the processes of mining, fabrication, in-use dissipation, collection, sorting, and remelting. We are also doing this simultaneously for multiple metals at the same time, because we want to know to which extent secondary materials are being contaminated by other metals, which we could not do if these were material flow analyses one metal at a time. And we want to know ultimately what are the longevity as well as the circularities of metals. This whole model is implemented using the dynamic material flow analysis open framework as developed by Stefan Pauliuk and Nico Heeren, called ODIM. And we use in that dynamic material flow analysis data from Japanese input-output tables as well as ISIE-base. We also use MFA data and Japanese recycling process data, so to speak, mechanistic information. And all this leads into a global, planetary, one-region model for the material flows of all durable goods in terms of metal-relevant products. We go from extraction to recycling through the whole economy, through all stages of the metal cycle, and we do that simultaneously for 7 metals. These metals are aluminum, chromium, iron, nickel, copper, zinc, and lead. And here are the processes that we consider while doing this dynamic MFA. Materials are first extracted. They enter the mining stage. From there, they are fabricated into durable goods and end-use products. This is this so-called sector split, as Jan called it. They are then entering a use phase, during which they may be dissipated also, for example, through fertilizer use or something like that. Or after a specific lifetime, they are exiting this use phase once again. They can be collected. They don't have to be, but they can be collected. If they are collected, then they are sorted into different scrap types, which are then allocated to remelting processes. The remelting processes are important for us because here thermodynamics happen, because different metals act differently in different remelting processes. And the remelting process ends up with a secondary material, which can then once again be allocated or splitted onto the fabrication processes, and then the metals enter another use phase and the cycle starts again. And at each of these processes, dissipative losses can happen. Ultimately, because we only trace the production of 1 year, so the extraction of 1 year, ultimately metals will be dissipated at some point in the future. If we can delay that for a longer period, then this is good, and this is good for the circular economy. We use the sector classifications basically as an ISIE base for the products, from beverages to construction work. These are the 11 product sectors that we consider. And we have a number of scrap types, remelting processes, and secondary materials, which we can then differentiate with specific transfer coefficients. Now, where do input-output information come into play? So we use the waste input-output MFA methodology, as mentioned by Jan already, to, for example, quantify the initial material flow and thereby the material content, for example, of aluminum in construction work in the first year, in the initial time period. And we do that by a combination of ISIE base as well as the Japanese input-output table. The Japanese input-output table, as developed by Ono and colleagues, has the advantage that it is very disaggregated, in particular for the steel sector. It is a high resolution of 619 products, whereas the ISIE base only has 200 products. So we use the ISIE base for the global final demand, but we use the Japanese input-output table for the detailed waste input-output material flow analysis methodology, including the mass filters and the yield metrics, yield ratio matrix, as defined as in a publication from Nakamura and colleagues 2007. So thereby we can quantify both sector splits from this waste input-output MFA as well as the material content in the first year. Because it is a dynamic material flow analysis model, of course, we also use a population balance model here in this case. So we only have one inflow in the beginning, and then we trace all the cohorts afterwards in a what-if scenario. So what if the current recycling rates, collection rates, etc., stay with us for the next decades? At which stage would these metals be dissipated in the future? And we use Weibull distribution lifetimes for this, also considering that during that use phase, in-use dissipation happens for some metals. For example, zinc from zinc-coated steel could be dissipated already during the use and is then unavailable for collection after the use phase. Now, what are the results? So one way to display the results here in this case is these stock graphs for individual elements. So we can trace the aluminum that was produced in the initial time period, here year 0, and look in which sectors from the ISIE-based sector classification the in-use stock is still present after 50 years, after 100 years, and so on. These are these line graphs here in the bottom left. After a long period of time, this in-use stock will be totally gone into dissipation. And we can trace over this time which of the processes was responsible for dissipating the material. And we do that also considering a Monte Carlo simulation to check for uncertainty. Another part of the results that we can show is how much mixing occurs during the scrap allocation, including, for example, wrong sorting of materials, and during the scrap allocation and remelting. So the remelting processes produce then secondary materials once again, and thereby we can produce these Sankey diagrams here, which show us the mixing of the different 7 elements throughout scrap allocation and remelting processes. Ultimately, what we want to do is we want to calculate circularity and longevity. What do these 2 terms mean for the case of metals? Circularity means how many product lifetimes does one element statistically live through before being finally dissipated and therefore being unavailable for recovery. And longevity means what is, once again, statistically, the average lifetime. So how many years pass until this moment of dissipation. And we can, from these 2 values, circularity and longevity for the various metals, plot this scatter plot here in this case, where we plot the longevity versus the circularity. And once again, we do a Monte Carlo simulation for this, so we can also give a Mahalanobis distance ellipsoid as an approximation of the confidence region. So what are the key findings? We have a waste input output material flow analysis calculations to estimate transfer coefficients like the sector split or primary and secondary materials that we require for the DMFA model. We see that there are low circularity and short longevity for zinc, for example. Of course, this just within this selection of 7 metals, with about 2 applications as a statistical mean and about 50 years that zinc is living through until dissipation. We see high circularity and long longevity for nickel with 5 applications in 120 years. For lead and aluminum, it strikes that the cycles are rather short, so only 16 years on average per cycle, whereas for iron, this value is about double the size, so 35 years per cycle. And we see a high correlation between circularity and longevity. Maybe that was expected. And we can also see that there's a statistical contamination. Of course, this is only statistical because only during time there will be more primary production, so there will also be dilution once again. But statistically, there's a contamination for copper and aluminum, which goes into iron, and iron, for example, which also goes into aluminum over time. And we see also things like, for example, a shift of wrought to cast aluminum over time. And with that, thank you very much for your attention, and I'm open for any questions.
Thank you very much. Very clear and great presentation. I see some claps and the floor is open for any questions people might have. We are already a bit far advanced in time, so we can turn this also into a broader discussion if people would like to. But first, maybe we have some questions for Christoph and his work directly. People are leaning into the screen to read your figure, which is always a good sign.
Yeah, I have a quick question. Thank you for the great presentation. And I think this is a very important topic for the recycling. For the longevity, one thing I understand is that there's a consumer behavior that may affect the longevity, whether it's returned or not. So how does that factor into the calculation of longevity?
So the longevity in our model is modeled per product sector. And as mentioned, the product sectors here are rather broad. So construction work, metal products, motor vehicles, and other transportation equipment, for example, are just 4 sectors. And these are modeled with Weibull distributions here, using data from the Lives database from Ichiro Daigo and colleagues. I think this was developed, also Japanese data. But the database is Japanese, but the data that they collected was Japanese and global.
So it is reflective of actually what is happening in the economy, and it's accounting for that.
Yeah, and this is historical data of how the products are how the lifetime distributions are typically estimated, but we do not have changes to the lifetime distributions or circular economy measures like reuse or something like that implemented into this model.
Okay, thank you.
Well, I guess from this model and this framework, you could explore the effect of different measures as a kind of next step.
Absolutely, and this would be totally in line with what, for example, Stefanie Klose and Stefan Paulik have done for just copper. So they had a matrix-like model, and they did it for circular. They did a what-if scenario analysis for the copper sector alone. But this is definitely possible.
Yes. Okay, so we have a question in the chat from Joe. Regarding dissipative loss in circularity, is there a threshold of dissipation or the like that must be reached before the material is no longer considered circular? How is this dissipation threshold determined?
So in this case, we did one could possibly say we did a top-down approach on quantifying the dissipation rates. We used basically collection rates, sorting rates, production yields, for example, to quantify what are the losses in each of the processes. We do not quantify what are the real mass shares of, for example, aluminum in not exactly aluminum, like copper in aluminum scrap types or something like that. We do not do that bottom up again, because we only trace the metal throughout time, and to quantify the real material flow content or the material content in a specific scrap type, for example, we would have to quantify this with the next cohorts as well and add these values up.
Okay, Joe is happy with your answer. That's always good. We have a hand from Jan. Please go ahead.
Yes, thanks. I have a question regarding uncertainty. I don't know if I missed it, but I'm of course interested in how far uncertainty is also represented in the end-use split or sector split. So did you also model uncertainty for that? And on which basis? Like, did you gain uncertainty data from the input-output tables, or did you assume distributions or such?
Yeah, what we technically do is we have a Dirichlet distribution, which means a multivariate beta distribution, which we draw as samples in the Monte Carlo simulation for the sector splits. This is important because sector split, of course, can't be bigger than 1 in the sum. You can't allocate more material than you have. And therefore, you use this Dirichlet or multivariate beta distribution to do that. The level of uncertainty for this is estimated based on the data quality that we had, which was different levels. So for some values, for example, we had to make assumptions. Then we had a high level. So we do 3 different levels of uncertainty levels that we consider in each of the distributions and the samples that we draw. And for the already verified and reused material flow analysis data, for example, for steel, these were lower uncertainty values than we had for other sectors, for example, for zinc.
Cool, thank you.
Thank you very much. We are already quite far advanced in time, so if there are any more questions or general comments from the audience, I would be happy to have them. Otherwise, I have heard that there is a happy hour coming. Sadly, there is no bar to go to, so you have to imagine your bar. But it's still a happy hour. It still counts, I have been told. So last call for actual questions before going into a more relaxed atmosphere. I think everybody's head is quite full with all the great content we have seen. Then I would thank all the presenters very much for the great presentations, really exciting work, really exciting crossovers and inspirations on both sides or in both research streams. And I'm very happy to see this progressing, and maybe some of you even got some new ideas and new potential collaborations or people to talk to at least out of this. I see a lot of claps, which is wonderful. I will give you like a real life clap. And with this, I officially close this session. And I also officially open the happy hour part. Let's see how that goes. This is now a bit open. We can also have breakout rooms for people who want to have a direct chat. You can just let me know. People are logging out as it's already late, at least for the European participants. Let's see who stays.
I'm saying goodbye, Dominic. Thank you for hosting this great session to the presenters. It was really nice to listen to you. Bye.
Thank you all. Goodbye, everyone. Thank you. Nobody is obliged to say. Even the presenters are not obliged, so please don't worry.
First of all, thanks Dominic and Tamir for inviting us. I'm not quite sure how the